Now let's talk about the maximum work in a reversible process. Now for this, let us consider a closed stationary system undergoing a reversible process R. So let's focus on this particular diagram, that is a TS plot. Okay, and you have a system which is undergoing a reversible process R. So this is the process from 1 to 2, which is going through this reversible path. Now the surroundings, if you look at this particular diagram, this is the system which is depicted by a TS plot in this diagram going through a reversible path. Okay, so this is indicating from state 1 to state 2 you have a process. Okay, and the surroundings are at the conditions P0 and T0. Now if you apply the first law of thermodynamics on this process, you will have, so let us say in this the heat interaction is QR. This is equal to U2 minus U1 plus WR. So that is the work interaction in this reversible process. Now the process were irreversible, it would have been represented by a dotted line. So this dotted line is the irreversible path I, and it is connecting the same equilibrium end states 1 and 2. Now if you talk about this particular irreversible path, and let's apply the first law of thermodynamics for the process through the irreversible path, I would have Qi is equal to U2 minus U1 plus I'll have some irreversible work. Alright, now if you compare these two equations, I can easily strike off U2 minus U1, isn't it? So I will have QR minus QI is equal to WR minus WI. So this is what I get after subtracting these two equations. Now we know that the entropy change of the system, this is nothing but S2 minus S1. Now if you look at the heat flow direction and the work flow direction, we have some heat which is flowing into the system, okay, and we have some work which is coming out of the system. Alright, so the heat is flowing from surrounding into the system. So the surroundings are losing heat. This means that the delta S for surroundings is, this is equal to minus Q upon T0. Now if you remember the second law, the delta S of the universe, this is always positive, that is more than or equal to 0. Okay, and this is equal to 0 for a reversible process. Now this means, let's make up two cases because we have two processes, one is reversible and the other one is irreversible. So for reversible process, delta S universe, which is equal to delta S system plus delta S surroundings, this will be equal to S2 minus S1 minus Q upon T0. This should be equal to 0 because it is for a reversible process. Now if you look at this particular equation, and let's put R over here because this is for a reversible process. From this particular equation I will get the value for QR, which is nothing but T0 into S2 minus S1. So this is the value for QR. Now if you talk about the irreversible process, okay, for irreversible process, delta S universe, this is equal to, let's write down universe better. So this is equal to S2 minus S1 minus Q upon T0. This is a positive value, isn't it? And this is the irreversible heat flow. So this gives us the value for Qi, which is equal to, or you can say this is not equal to but less but greater than, this is greater than, or Qi upon T0 is greater than, you would have minus S2 minus S1. Okay, so now if you change the sign on the left hand side, the inequality sign would change and you would have Qi less than T naught into S2 minus S1. Now if you look closely, this particular expression is the expression for QR. So this can be substituted over here. So you will have a relation that Qi is less than QR. Fair enough. This means the heat interaction in an irreversible process is less as compared to the heat interaction in a reversible process. Okay, so now if you go back to the equation, that is this equation, and rewrite it, okay, so you would have QR minus Qi is equal to WR minus WI. Now because QR is greater, so the difference between QR and Qi would be a positive value, isn't it? So this is a positive value. This means this difference will also be positive. Okay, so this difference being positive would result in this kind of a relation, that is the reversible work is higher as compared to the irreversible work. So if you write it down in the form of a statement, we can say that the work done by a closed system by interacting only with the surroundings, okay, at P naught T naught is in a reversible process is always more than an irreversible process between the same end states. Right, so this is a comparison between the work done in an irreversible process and the work done in a reversible process. Okay, now after this, let's do a very small analysis of the work done in all the reversible processes. Okay, so for that, let's draw a diagram again, and that system or that diagram, let's make that diagram like this. Okay, so this is, you can say, a TS plot again, and we'll have two end states, 1 and 2. All right, and we have two reversible paths. This is a reversible path R1 and this is a reversible path R2. And if you depict this in the form of a simple schematic, this is the system. Alright, and it is going from 1 to 2, and the surroundings are at temperature and pressure P0 and T0. You have some heat interaction and you have some work interaction. Now, if you look at this diagram, it shows two reversible processes R1 and R2 between the same end states 1 and 2. And this is basically representing a closed system which is only interacting with surroundings. So the only interaction of the system is with the surroundings at the temperature T0. Okay, now let us reverse one of these processes. So you have or you can say one of the paths, I would say. So let's reverse R2. So you would have, let's reverse this and make it in this direction. So I am reversing path R2. So instead of the process 1 to 2, it now becomes 2 to 1. And this is now representing a cycle 1 to 1. Okay, so this system is now actually going through a cycle, or it is executing a cycle 1 to 1, and it is producing some network which is represented by the area enclosed, okay, by exchanging energy only with one reservoir, and that reservoir is the surroundings. And that cannot happen because a cycle has to exchange heat with two reservoirs. Now this is only a single reservoir which is a surrounding at temperature T0. Now this violates the Kelvin-Planck statement. Okay, so this means the two reversible processes, that is R1 and R2, they must coincide and produce equal amounts of work. So this is very, very important. Okay, initially what we said, that we have two reversible processes, R1 and R2, or you can say two reversible paths, R1 and R2, but they cannot be two different paths. They have to be the same path. Okay, because it eventually violates the KP statement. So the statement can be remembered as this, that is, the work done by all or in all reversible processes, in all reversible processes is same. Okay, why same? Because it violates the KP statement, because if you take them as separate paths. Okay, so one more corollary of the same statement, or one more explanation of the same statement would be that the two reversible processes must coincide. You cannot have two different reversible processes between the same end states. Okay, so they must coincide and produce equal amount of work, Okay, so this finishes this topic, in which we found a relation between the reversible work and the irreversible work, and we also proved that the work done in all the reversible processes is same, and the reversible processes between the same end states must coincide. Okay, so this finishes this video and this analysis. Now let's talk about the reversible work by an open system exchanging heat only with the surroundings.